This is the 8th lecture from Philosophy 201, Introduction to Logic. And today we're going to go over the proof rule and proof strategy that's called famously reductio ad absurdum, which is a Latin word, a Latin phrase, which literally means reduction to absurdity. However, in the case of formal logic, it means reduction to a contradiction. So it's proof by a contradiction. This is, on the one hand, one of the most powerful methods of proof that you can use in logic, and in many ways you might say it's the method of last resort. So when all else fails, often reductio ad absurdum will save the day. So the idea behind reductio ad absurdum is quite amazing, it's quite ingenious, but it takes a little while to get the hang of it. The idea basically is, from a set of premises, if the negation of something follows from the set of that premises, one way you can show that is if you assume what you don't want to prove, assume the opposite of what you want to prove, and then derive a contradiction. Okay, so let's just go straight to an example of that. Okay, starting out looking here on the left-hand side is a informal sketch of a proof by contradiction, a proof by reductio ad absurdum, and then what's there on the right with the blue I'll come back to because that's the formalization of the proof. Okay, so what I'm going to show now is I'm going to show that not P is a logical consequence of not, in parentheses, P or R. So we know that means neither P nor R. So in a way that's obvious, right? If you say neither P nor R, of course it follows that not P. So how do we show that? Because if you look at not and then parentheses P or R, there's nothing you can do to it. There's no rules that can touch it, no rules that can touch it in any useful way because the or is inside the parentheses. Okay, so here, imagine for a minute you're in an informal setting, and once again, imagine that your conversation partner is someone who refuses to accept common sense. So someone, you say neither P nor R, and you want to convince the other person, so not P, and the person says, but why? Let's take it down to rules that are simpler that we already agree on. So here's what you might do. You both agree that it's not true, neither P nor Q. So not parentheses P or Q. Now your conversation partner has agreed with you that you may always suppose new things as long as you both agree that it's just a supposition. So suppose you say to your conversational partner now, you're not convinced that not P from neither P nor Q. So suppose that P were true. Suppose that P were true. Now you'll see what I've done here is I've indented line 2 to indicate that it's a new supposition. So it's a sort of under this supposition, suppose that P. Now, under that supposition, everything becomes like it was before. That is, we can, from the supposition of P, infer that P or Q. That's just or introduction. Now, lines 3 and 1 then give P or Q and not P or Q. A sentence conjoined with that very same sentence is negation. So that's an explicit contradiction. I'll mark that to be totally clear. So here's a sentence, P or Q, let's call that phi. Here's that same sentence, P or Q, but it's negated. So we have an instance here of phi and not phi. So under the supposition of P, a contradiction follows. And now the rule of reductio ad absurdum says, if a contradiction follows from something, then that thing's not true, so not P. But you'll see what I've done there on line 5 is I've unindented back out to show that not P follows from the original line 1, not P or R, not P or Q, that is neither P nor Q. Okay, so now let me zoom out and show you how exactly that thing that was just done, that argument, corresponds to a fully formal proof. Okay, so line 1, nothing new. Neither P nor Q is an assumption. Line 2, nothing new. Actually, Nothing new through lines 4. Those are all things we were permitted to do before today, before this module, this session. So, but what happens, the new thing is on line 5. Line 5 says, what we've seen is the supposition from line 2 led to a contradiction. So therefore, we're now permitted to infer the negation of the supposition on line 2. And let's talk really quickly about dependency numbers. Okay, so what we do in reductio ad absurdum, so we see we need 2 lines for reductio ad absurdum. Here we have 2 is the supposition, 4 is the contradiction. So 1 assumption, 1 contradiction. Then the way we tabulate the dependencies on the left-hand side over here, what we do is we carry down the dependencies of the line of the contradiction, except we get to remove, if it occurs, we get to remove the supposition. So that's exactly what I did. I carried down 1, 2, but took out 2, which was the assumption of the thing that we thought is not correct, from which we were going to derive a contradiction. So that's the rule reductio ad absurdum. Okay, as with our other rules, the way you really understand it is by using it. So I'll give you some more examples now. Okay, let's show now, this is a argument sometimes called weakening, because you're deriving something that's ostensibly weaker than what you assumed. So not P, derive not P and Q. So of course, not P and Q is weaker than not P, because you're saying it can't be that both P and Q. Okay, so if it can't be that P, then surely it can't be that both P and Q. So how do we do that by reductio ad absurdum? Okay, here I begin with my assumption as usual. Okay, now thinking strategically, I want to show that P and Q cannot be true. So what I can do by reductio ad absurdum is I can assume that P and Q is true. Now I can always assume that. As with any case of the rule of assumptions, the question is, will it be a useful thing to assume? Do I have a plan? And in this case, my plan is to derive a contradiction. So what I'm going to do is I'm going to, on the right-hand side, write in something here that is actually not part of the proof, but is a hint about what I'm doing. That is, I'm trying to get a contradiction. I'm trying to show that the assumption on line 2 is inconsistent with what happened on line 1, with what we have on line 1. Okay, in this case, it's pretty easy to see how that contradicts line 1, because line 2 gives us P. And so now we have P and not P, 3, 1, and introduction. Okay, so now the assumption on line 2 has led to a contradiction. So I can write the negation of what the assumption on line 2 was. So that's 2 to 4, reductio ad absurdum. And once again, I carry down the dependencies. I'll mark this clearly here in a different color. So I'll carry down the dependencies of the line on which I got the contradiction, but I look back for the dependencies of the line where I made the assumption, and I get to take that away. So it gives me at the end just dependency on 1. And as usual, I go back and check, what have I shown? So what was on line 1? That was not P. What was on the final line, line 5? Not P. Sorry, that was not P on line 1, not P and Q. So here's what I've shown as I wanted to do. So not P and Q follows from not P. Okay, so this next proof is famous, troubling, and easily provable by reductio ad absurdum. So this actually is one of these ones that has bothered people since the Middle Ages, in fact. And they gave it a name, the medieval logicians. They called this ex falso quodlibet, which means basically from the false, anything follows. Okay, I'm not going to go all philosophical right now about this, but in short, don't worry. This doesn't show that our logic is bad. It shows that if your premises are bad, anything follows validly. That doesn't mean there's a sound argument. It means there's a valid argument that could never be sound, because it can't be sound because the premises can't be true. Okay, but let's forget philosophy for a moment and just see how we prove this. Okay, so line 1, I have P. Assumption, line 2, not P. Assumption. Okay, now I want to prove Q. This is a very strange setting because Q doesn't occur on lines 1 or 2. Where is Q going to come from? Now, what we see here is, and this is going to seem like an abuse of the rule, reductio ad absurdum. Now that I already have a contradiction between lines 1 and 2, I can assume the negation of anything I want to get and do reductio ad absurdum backwards. Our rules don't know the difference between backwards and forwards, except that you can only, at any stage, draw inferences from what has gone before, but our rules don't know order. So our rules don't know, did I assume something and then get a contradiction, or did I have a contradiction and then assume something? Okay, so in this case, the strategy is I assume not Q, wanting to get a contradiction, knowing I already have one in store that I can bring out. So here's my assumption, not Q. Now I just create my contradiction, P and not P. So lines 1 and 2, and introduction. Okay. Now the following is a legitimate application of reductio ad absurdum, not Q. That is from 3, 4, reductio ad absurdum. So 3 is an assumption, 4 is a contradiction. That's an okay case to use reductio ad absurdum. Now let's calculate dependencies correctly. So what we do is we copy down these. So 1 and 2. And now we can take away the dependency of the assumption 3. If it occurs, it doesn't occur here. So there's nothing to be done. We just end with dependencies 1 and 2. So the final result is exactly as we wanted. It's P, not P. Oops, there's a missing line here. I haven't finished the proof yet. Let me go back. So what I meant to do here was finish by changing that not Q to Q. So from 5, double negation follows from 1, 2. And now I have what I wanted to prove. So P, not P, gives me Q. Okay. So that's the end of this proof, ex falso quodlibet. Now, however, I'm actually going to quickly create another proof just to show the power of what we've done. So I'm going to go back now, erase this little mark I did at the end. I'm going to add a line to this proof. So here's something that I can do is I could, going back, looking at the assumption on line 2 and the assumption on line 1, I can now turn from the assumption on line 1 and the derivation of Q on line 6, I could turn that into a conditional proof. So what I can do now is I can go if P, then Q, from 1 to 6, conditional proof. How does that change the dependencies? So I take the dependencies on line 6, I take away the assumption that occurs on line 1, so 1, so now I get just 2. Okay, so I just added one line of the proof here, and now I've proved something new. And what have I proved? I've proved that from not P, it follows that if P then Q, which you know already because that's negative paradox, right? Negative paradox says from a negated sentence, you can infer the conditional. So from negation P, you can infer if P then Q for any Q whatsoever. So negative paradox is a quick result of ex falso quod libet. Okay, so now we have something that's a little bit more complicated, but is actually quite important. So it's quite important for us to know and to be able to demonstrate that our conditional is equivalent to a disjunction and a negation. So in other words, if P then Q is actually equivalent to not P or Q. I won't right now at the moment give you a proof from not P or Q to if P then Q. I'll go the other way, from if P then Q to not P or Q. Okay, so beginning this proof, assumption if P then Q. I'm going to move this assumption further to the right, knowing actually this proof is going to be somewhat long and complicated. Okay, so now we need to do a little bit of strategizing here, because if you look at the right-hand side, not P or Q, I've told you before that when you're writing a proof, so you're writing a proof starting from some premises, going down, trying to get some conclusion, your brain should be doing two things simultaneously. You should be both asking yourself, what can I get from those premises? Asking yourself, what do I need to get that conclusion? And then gradually try to stitch those together into the middle. Okay, so if you just look at the premise here, if P then Q, by itself, there's not much useful you can do with that. You could, of course, do double negation. You could do and introduction with it on itself. Why would you do that? There's no plan. You need to have a plan. What can I do to this thing that will get me my conclusion? Looking at your conclusion here, not P or Q, ask yourself, what would I need to get not P or Q? Now, it may be tempting at this stage to say, I know that or introduction would give me not P or Q if I got not P, for example, or if I got Q. However, if you think about it for a minute, it should become clear that you can't get not P from if P then Q. Okay. From if P then Q, it does not follow that not P. It also doesn't follow that Q. It does follow, strangely enough, that either not P or Q. Okay, so there's no way you can get to the destination here, the sentence not P or Q, by passing through not P or Q. So we need a more holistic strategy here. Now, if you sat here for a long time, sat and thought, how can I get it? How can I get it? You may eventually become frustrated and say, I'm going to go to my last resort, reductio ad absurdum. And in this case, that would be a good choice. And let me explain why you could know that this was a good choice. So if you assume not P or Q, assumption, trying for reductio ad absurdum. So I'm going to put goal is to get a contradiction. Okay, now, earlier in this session, we showed that if you have a negation symbol outside of P or Q, so not P or Q, neither P or Q gives you not P. Neither P nor Q gives you not P. Neither P nor Q also gives you not Q. So that actually is an instance. If you did both sides of that, you get something that's called De Morgan's laws. So not P or Q can be used to derive not P and not Q. Okay, in the same way, not P or Q can be used to derive P or, sorry, this is not or, but P and not Q. Okay, now, if that's too fast for you, just hold on. We'll do it again in this proof. So what I'm thinking now is if I look at line 2, I'm going to be able to get P and not Q from line 2. And if you think about it, you'll see that P and not Q definitely contradicts line 1, because P together with if P then Q gives you Q. And then so you'd have Q and not Q. Okay, so that's my proof strategy to get a contradiction here. So now when I go through the details, that's going to be in the back of my mind. Okay, so what I'm going to do here is I'm going to start by just explicitly showing I can get P. So I assume not P. Okay, and that gives me a contradiction, not P or Q, and not P or Q. So that's 4 and 2, give a contradiction. Okay, so that means not P follows from 2. Oops, so actually there's a mistake in what I just did. Let's be very careful here. This was an attempt to show that the assumption of not P after you had already assumed not P or Q is going to give a contradiction. So P follows from line 2. Okay. Now, what I can do, now that I have P, I can use P together with line 1 and do modus ponens and get Q. And that is again going to give me a contradiction with line 2. But in this case, it's going to give me a contradiction that depends, a contradiction that only depends on the assumption of 2 after having 1 in place. So what I'll do is I'll write Q from 1 and 7. Okay, so finally, at line 10, we've got a contradiction now that follows from 1 and 2. So I can put now not P or Q. So this is 2 to 10, reductio ad absurdum. And of course, this is equivalent to not P or Q. So line 11, double negation. Here we go. So finally, after all these steps, we know that not P or Q follows from if P then Q. Okay, last one more for this session. So this is another example of a proof that has no premises. So here we're going to show that P or not P follows from no premises, which means our very first line is going to have to be a very clever choice of something that in the end will actually discharge that assumption, because in the end we'll have no assumptions. Now, this is just like the previous one in the sense that if you try to somehow get P and then do or introduction, it's not going to work. You can't prove P. You can prove P or not P, but you can't prove P. You can't prove not P, but you can prove P or not P. So we're not going to try to get P. We're not going to try to get not P. We're just going to see that assuming the negation of this thing leads to a contradiction. Okay, so if we assume P or not P, we're going to see that we end up with a contradiction. Okay, now my strategy here is, again, I'm going to think in terms of De Morgan's. So in other words, not P or not P is going to give me both not P and not P, which is equivalent to P. So it's going to give me a contradiction. Okay, so that's the idea in the back of my head I'm using here. So I'm going to assume P. This gives me P or not P. And now I have a first instance of a contradiction. So that leads to the contradiction that both P or not P and not P or not P. 3, 1, and introduction. Okay, so 2 led to a contradiction. So now we get not P from 2 to 4. Reductio ad absurdum. So now we see that's sort of the first bit of De Morgan's. That is, we see that not P or not P leads to not P. Okay, but now line 5 is also going to give P or not P. So 5 or introduction. Once again, 1 leads to its own contradiction of itself. So we have P or not P and not P or not P. 6, 1, and introduction. So not P or not P. 1, 7, reductio ad absurdum. And now this is one of these tricky things, right? Where the way we calculate the dependency numbers for 8 is we would carry these down here, but then we get to take away the dependency of the assumption that led to the contradiction. In this case, the assumption is line 1. So we take the dependencies that is just 1 and we take away 1. So it leaves us with a blank. So I'll just sort of put a slash mark in here to indicate nothing's left of the dependencies here. Good, because now we're going to finish this proof. P or not P, 8 double negation. No dependencies. Okay, so therefore, P or not P is true no matter what. It follows from no premises at all. And this is the famous law of excluded middle that we've just proved. Okay, so that's it for reductio ad absurdum. Remember again, the idea behind reductio ad absurdum is if you want to show something is false show the negation of something from a collection of premises. Imagine almost that you create a duplicate of yourself. So the duplicate of yourself believes all the things you believe, but you program into that duplicate that they also believe the opposite of the thing that you want to show is true. And then this duplicate of yourself, you want to see that they end up believing a contradiction. That's the idea behind reductio ad absurdum. You take the things you currently believe, you add the opposite of what you want to show, and show it leads to disaster, namely a contradiction. And that's enough, according to reductio ad absurdum, to see that, to prove the result you wanted.